So now we're going to look at how do we solve other types of first order differential equations. Realize that not all first order differential equations are going to be separable. We already saw one that were linear. Not all are linear. So how do we solve if they're not separable and they're not linear? Well, the answer depends on what kinds they are. Just as with linear and separable, it just depends. You have to look at all these different processes. So we'll look at another type. This is what we call an exact equation. And I don't know if you're ever going to find the exact equation, but it has a neat property if you do have an exact equation of how we solve these. So first we need to find what the exact equation is. This is theorem 2.4.1 if you want, or give it a name. We're going to let m of xy and n of xy be continuous and also have continuous first partial derivatives. Then if we happen to have m of xy dx plus n of xy dy equals 0. So let's just say this is my differential equation. It's not written exactly in the form that we've used to, but we can just divide through by dx and you get kind of the same thing we've had before. So we still have a first order differential equation because it's just dy and dx. It's an exact equation if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Now, I wouldn't memorize this. I would just kind of trying to think about this. M is the function that times the dx, but we're going to take the partial derivative of m with respect to y. N is the function that's with the dy, but we're going to take the partial derivative of m with respect to x, and we're going to see if they are equal to each other. If they are, it's an exact equation. That's all we're looking for at the moment. So let's determine if the following are in fact exact equations. The first one we're going to have is the sine of y minus y sine of x dx plus the cosine of x plus x cosine y minus y dy equals 0. So here is my differential equation. My m again is the one that's with the dx. We're going to take the partial derivative of m with respect to y. So the partial, no, I'm not going to write the m in there, sorry. So the partial derivative with respect to y of my sine y minus y sine x. Now, if you don't know what a partial derivative is, it's not a big deal. It's really, well, it is a big deal, but it's not a big deal for you right now. We can do this. We're just going to pretend the other variables are constants. Y is my only variable I'm dealing with. You'll get more into what a partial derivative is in other classes, but for this class, all we think about right now is that the partial derivative of with respect to y means y is my variable and everything else is a constant. So the derivative of sine of y is cosine of y. The derivative of y sine of x is a constant because y is my variable because we're doing the partial derivative with respect to y. So this sine of x, even though you think sine of x is not, it can be thought of as a constant in this function. So replace it with the number 3 if you want to. The derivative of 3y is just 3. So the derivative of sine y times sine of x is just sine of x. Now we're going to take the partial derivative with respect to x of the n, which the n is the one attached to the dy. So cosine x plus x cosine y minus y. We're going to take the partial derivative with respect to x. And again, that means x is my variable, everything else is a constant. So the derivative of cosine x is minus sine x. The derivative of x times cosine y, again, that cosine y is a constant. So it's really the x is the only important thing. The derivative of x is 1 times whatever constant's there. So plus cosine y minus y is a constant, so just 0. So we end up with sine of x plus cosine y. And notice sine of x minus sine x plus cosine y is the same as cosine y minus sine x. So these do in fact equal, so they're exact. Let's try another one. Let's try the 2y times 1 over x plus cosine of 3x all times dy dx plus y over x squared minus 4x cubed plus 3x I'm sorry, 3y times sine of 3x equals 0. This is my differential equation this time. I notice that I have this dy and this dx together. I'm going to go ahead and multiply through by the differential dx. So I end up with 2y minus 1 over x plus cosine 3x dy plus y over x squared minus 4x cubed plus 3y sine of 3x times dx equals 0. So reason I did this is I wanted to kind of figure out what was my m and what is my n. If you need to, go back. I need to because I always need to. My n is the one attached with the dy. My m is the one with the dx. So I want to do the partial derivative of my m with respect to, going back here, with respect to y. So we're going to take the partial derivative of the m with respect to y, but the m is the one attached with the dx. So we're going to have the y over x squared minus 4x cubed plus 3y sine of 3x. That is, in fact, my n. I'm going to take the partial derivative of that with respect to y. The partial derivative of y over x squared with respect to y is just 1 over x squared, because x squared, again, is a constant. You don't need to use this quotient rule here. The derivative of y is 1. So I get 1 over x squared. The derivative of minus 4x cubed is 0 because it doesn't have a y in it. It's just a constant. The derivative of 3y sine of 3x, the derivative of y times any constant is just the constant, and all that other part's a constant. So plus 3 sine of 3x. Let's do the partial derivative with respect to x of your n, which the n is the one attached with the dy. So it'll be 2y minus 1 over x plus cosine of 3x. Again, x is my variable. 2y has no x in it, so it's a constant, so its derivative is 0. The derivative of minus 1 over x is 1 over x squared. And the derivative of cosine of 3x is plus, or actually minus, 3 sine of 3x. Uh-oh. The partial derivative of m with respect to y was 1 over x squared plus 3 sine of 3x. And the partial derivative of m with respect to x is 1 over x squared minus 3 sine of 3x. They are not equal, so they're not exact. So now that we know if something is exact or not exact, we can go ahead and use this to solve an exact equation. We're going to find some function, f of x, where the partial derivative of f with respect to x is m, and the partial derivative of f with respect to y is that n. The biggest thing that people have problems with when they're doing exact equations is they get messed up on which partial they're doing where. Notice when I was trying to prove it was an exact equation, I did the partial derivative of m with respect to y. I did the partial derivative of m with respect to x. But when we're going to solve them, we're actually thinking of finding some function. And when I take its partial derivative with respect to x, I get m. And when I take its partial derivative with respect to y, I get n. So ignore what we did before to prove it was exact. You can kind of almost think of it as you're doing the second derivative. And remember, your second derivatives of the second derivative of f with respect to x and then y should be the same as the second derivative of f with respect to y, then x. That's why they have to equal each other. That's why we change the letters we're doing. So try to just think about that that's what you're really doing here. But we go to use this to find this, we're actually going to solve these kind of differential equations in a way, partial differential equations, sort of. So we're going to solve sine of y minus y sine x dx plus cosine x plus x cosine y minus y dy equals 0. Now this is actually, from the first example, this was the one that was exact. So already know this is exact. If you didn't, you'd have to prove it's exact before we could do this method. So now we know this is exact. So we're going to look for some function f so that when we take its partial derivative with respect to x, we will get sine of y minus y sine of x. And when you take the partial derivative of f with respect to y, you'll get the n. And remember, the n is the one that's part to the dy. So you will get cosine x plus x cosine y minus y. Well, that's great. That doesn't seem like too much for us, but I'm going to think of this as kind of doing an integral of both sides of here, but the integrals with respect to x here. So this is the partial derivative of f with respect to x, which means I can think of it as what function, when I took its derivative, did I get this, and the derivative with respect to x. Well, think of it as the integral of sine of y with respect to x. With the integral of sine of y is a constant. So the integral of a constant is just x times sine of y, times that constant. Y again is a constant, so when we do the integral of sine of x times y, that y is just a constant, so it's just sitting there. So it's still sitting there, and the integral of sine of x is plus cosine x. But it could be that we could have a constant there. So we could, in fact, have some constant. Normally we just write plus c, but again, this is where understanding partial derivatives helps a little bit. If that constant is a constant with a y in it, then when I took its partial derivative with respect to x, I would have gotten 0, it would have gone away. So it's not just plus any old constant, it could be plus some function of y. Because when I take the partial derivative of some function of y with respect to x, I will get 0. We're going to do the same thing with the other one. We're going to take the integral of the partial derivative of f with respect to y, take the integral of both sides with respect to y. So we're going to get f is equal to, again, x is my constant, y is my variable. So we're going to have y cosine x. When I take the derivative of cosine x with respect to y, it'd be y cosine x. The integral of x cosine y with respect to y is plus x sine y. And the integral of y with respect to y is minus 1/2 y squared. Okay. Well, now I'm kind of noticing that there's a lot of similarities going on here and a lot of things happening here. And you go, well, it looks like I can figure out what things might be, but there could have been a constant here. So I'm wondering if there's a better way we could have done this than trying to find this partial derivative and try to compare. We now have this f equals x sine y plus y cosine x plus g of y. It will, if this is the solution, and it should be, then it should satisfy the other partial derivative. So instead of doing where I took this derivative, this basically integral again, I'm going to actually get rid of that. And I'm going to think about, because it kind of got me where I wanted to go, but it was a little complicated. So I want to think about now, what I'm going to do is take the derivative of this f that I just found with respect to y and compare it to this one up here that I have. So the derivative of this with respect to y, again, x is a constant. The partial derivative of sine of y with respect to y will be x cosine y. Well, again, taking the derivative with respect to y, the derivative of y is 1 times the cosine x, because cosine x is just a constant, plus the derivative of g with respect to y. Now what we're going to do is we're going to compare that to what we said it was originally. So when I go to compare this, I can now see that when I put this down here, I had the cosine x plus x cosine y minus y. Comparing these, I can see, oh, it looks like g prime of y is just equal to minus y. Because these two terms are exactly the same. They can think of them as canceling each other out. The only thing left is g prime of y equals minus y. So now we can find out what that g prime of y is, what that g of y is. G of y would be minus 1/2 y squared plus some constant. So we now have that my function is what we said it was, x sine y plus y cosine x plus that constant function g prime of y, or g of y, sorry, g of y, which we just found out to be minus 1/2 y squared plus c. And you could have done the way I was starting to do it, but I think this way is a little bit cleaner. Let's try one more. Let's solve x squared plus y dx plus 2 plus x plus y e to the y dy equals 0. And we are going to tell you that y of 0 is 1. So it's an initial value problem. And when I go to do this, the first thing I have to do is prove that it is in fact an exact equation before I start doing that method. So I want to take the partial derivative with respect to, I always have to go back because I always get this backwards, partial derivative with respect to y of the one that's attached to the x, so e to the x plus y. The partial derivative of that with respect to y is just 1, because e to the x, it just has x's in it, so its derivative is 0 with respect to y. Then take the partial derivative with respect to x of 2 plus x plus y e to the y. The partial derivative of 2 is, of course, 0. The partial derivative of x is, with respect to x, is 1. And the partial derivative of y e to the y is also 0 because it's all constant because it doesn't depend on x. So these are equal to each other, so exact. So that means that the partial derivative of f, okay, again, looking for this partial derivative of f function with respect to x is the e to the x plus y. And the partial derivative of f with respect to y is the 2 plus x plus y e to the y. Okay. So let's first kind of take the integral of this, basically think of it that way. So find out what f is by taking the integral of both sides with respect to x. The integral of e to the x is, of course, e to the x. The integral of y with respect to x is x times y, because y is just a constant. So the derivative of a constant is just x times that constant. Plus, again, there could be a constant there, but that constant could be a function of y. So we'll call plus g of y. Now let's take the partial derivative of that function that we just said we thought it was with respect to y. The derivative of e to the x with respect to y is 0. The derivative of x times y with respect to y is just x. The derivative of g is just g prime. And that's supposed to equal 2 plus x plus y e to the y, because that's what we said it was equal to right up here. So now I'm trying to find out what g prime is. So looking up here, we're going to now try to figure out what would g prime of y be equal to. Well, if I get rid of the x, I get 2, the x is canceled, plus y e to the y. So that's what my g prime is equal to. Now I can find out what g of y is by just taking the integral of this with respect to y. That's 2 times y plus y minus 1 e to the y. Again, you can use technology to find out what y e to the y is, or your table of integrals. I don't care. So now I know what g of y is equal to. Oh, plus c. Don't forget the plus c. So, whoops. So now I have that my f is equal to e to the x plus xy plus 2y plus y minus 1 e to the y plus c. A lot of times what we will do with these equations is we'll actually get them be e to the x plus xy plus 2y plus y minus 1 e to the y equals c. We're basically taking the level curve. If you know anything about three-dimensional calculus, we're basically just saying, let's take one level curve. Let's say this whole thing equals 0. And so then we can say this whole thing equals some constant. And it just gives us our level curves we're working with. From this, I can now use my initial condition. My initial condition that y of 0 was 1. So y of 0 is 1, which means x is 0 and y is 1. So we've got e to the 0, which is 1, plus 0, plus 2, plus 2 minus 1 minus 1 is 0, plus 0 equals c. And so that means c equals 3. So we now have my equation is e to the x plus xy plus 2y plus y minus 1 e to the y equals 3. And that's how we solve exact equations.